Okay, so yeah, I am part of the Department of Physics at IIT Madras, and I am part of something called the Center for Quantum Information, Communication and Computing at IIT Madras. So I was told that this is going to be an audience of maybe high school and undergrad students, and so I was told to kind of keep it more introductory, so that's what I have done, but we can get into details if you guys want. Just quick show of hands, how many of you are high schoolers here? I see, okay. So that's like class 11, 12?
Yeah,
11, okay. And the others are undergraduate students, some from CMI? Yeah? Okay. And you're all undergrads in physics, math or CS, is it? Alright, so hopefully some of the stuff is new for you guys, but maybe there's more new things for the school guys. Anyway, so what's this talk about? So I guess quantum computing has been in the news for a while now, and this is 2019 when Google first came up with this claim of supremacy, which is a word that we don't use these days anymore so much. We call it quantum advantage now, just to be because of the connotations of this word. Yeah. Is it still good? Yeah, so there's a lot of names that you hear when you read these news articles. For example, IBM is often in the news. Google again, early last year, claimed to have achieved a major milestone with their latest chip. But then there are other players in the field. There's a company called IQM, there's something called QEra, there's something called Amazon, AWS at Caltech. So there's all of these different names that you hear, and all of them claiming to be achieving breakthroughs maybe every few months. So for those of you who are not in the field, you're probably wondering what is this all about and why is it so much in the news. So I always like to start these talks with a disclaimer of this kind. So this is Serge Haroche, who won the Nobel Prize in Physics in 2012. He was in fact one of the pioneers of this idea of actually being able to measure and manipulate individual quantum systems. So quantum mechanics itself, as you know, is reputedly 100 years old, although it's unclear how they exactly date this field. But as of last year, United Nations celebrated 100 years of quantum mechanics and so on. But it wasn't until the late 80s or the mid 80s that people actually figured out how to control and manipulate single quantum systems, and that's what the rest of this talk is going to be about. It's about single quantum systems and how they can be thought of as resources for computing, right? But of course, there's a lot of hype in the field. It's in the news all the time. So always one has to take this with a pinch of salt. And I really like this quote that quantum computing is trapped between hype and hope. He said that in 2012. I think it's more true than ever today in 2026 as well. So what is all the hype about and what is all the hope about? So that's what I hope to tell you. So today we are in an era of what is called noisy intermediate scale quantum devices. You might have heard this acronym if you read the news again. So it's called NISQ. People like to say we are in this NISQ era. So this is what a quantum computer looks like today. So technically one should not really be calling this a quantum computer. So that's why I've said quantum devices. Sometimes you can call them quantum processors, but this is hardly a computer in the sense that we know and understand like what I'm using here. So what is this? Does anybody know what this picture represents? You've all seen this picture? Yes, this big chandelier-like object. What is this big thing? Sorry? A Google computer.
The thing which goes around.
The thing which goes around in the news is exactly correct, but what is this object, this real physical object, what is it? So it's something that's going to occupy like half this room, right? The scale of things you see with all these wires popping out and everything. But what is here? It's a quantum processor, yes, but where is the processor? Okay, maybe let me ask that question. Where is the computer here? Where is the processor? Okay, so the processor is sitting deep inside down here, okay, on a little chip of this kind, and this is a chip which has less than 100 qubits etched on it, okay, and what is down here is actually a very fancy refrigerator. It is what we call a dilution refrigerator. It's something that maintains whatever is inside it is at the temperature of liquid helium. Anyone knows what that is?
4 degrees of 4 Kelvin.
Kelvin, yeah, exactly. So it's of the order of about 4 Kelvin, right? So this little chip out here is your quantum processor, but it cannot work at room temperature. Okay, so it has to be put deep inside this dilution refrigerator with all these wires coming out, forming the control paraphernalia in order to access these qubits that are etched here, in order to manipulate their states, in order to read in, read out, etc. Anybody knows what kind of qubits they are? What you must have, if you've read the news, then maybe also hear this term, superconducting qubits. You heard of superconductivity?
Yes.
Okay, so superconductivity is a phenomenon that works only at extremely cold temperatures, and we need these objects to behave as superconductors. So what this qubit is actually something called as Josephson junction, and that's what forms the basic unit of a quantum bit here, and it has to be cooled down to extremely low temperatures, and so that's what the situation is today. This is what a quantum processor of today looks like, but you see we are kind of counting qubits or quantum bits here. We're saying 72, and then you look at other things. So Rigetti is another company that makes these things. So this is one of their chips which has one of the architectures which has 16 qubits. They like to do this modular fashion where they put together things with 16 qubits to form a larger processor. This is IBM's dilution refrigerator Q1 processor, as they called it, with 50 qubits. Of course, IBM today has many more qubits in their processors, maybe of the order of hundreds, maybe 400 qubits. But you see, the point is we are counting qubits. We are therefore not really at scale. We are at small scale or intermediate scale. And the other aspect of these processors or these chips is that they're extremely noisy. And I'll come to what I mean by noisy maybe towards the end of the talk. But what I'm going to do over the next 20 minutes or so is to help you understand what's going on inside these things from a mathematical or computational point of view, right? So we all know what a bit is. It's a unit of classical information. Mathematically, it's an object in a binary field which takes one of two values, 0 or 1. What is a quantum bit? Okay, so I suppose this is notation that some of you have seen, this kind of notation. So this is what we call Dirac notation. Maybe the high schoolers may not have seen it. So this is how I represent the states of a quantum bit, but all I seem to have done is to take the 0 and the 1 and put some funny symbols around it, right? So what is the meaning of putting these funny symbols around it? The meaning is that these are now no longer just scalars, these are no longer just objects in a binary field, they are actually vectors, okay? They are vectors in an abstract vector space, not vectors in the sense that we understand in the three-dimensional real space, although that is also an example of the vector space that I'm going to talk about, but they are vectors in a linear vector space. So what is the idea of being a vector if you think about it? So think about any point in this room. You know that it can be represented in terms of an x coordinate, a y coordinate, and a z coordinate. So this is what we call a three-dimensional real vector space, right? And every point in this room can be resolved in terms of 3 orthogonal axes. So in the same way, the quantum bit is an object that belongs to a two-dimensional vector space, not a 3-dimensional, but a two-dimensional vector space, a two-dimensional complex linear vector space. Complex because here in the real space, every point here is resolved in terms of an x, y, and z coordinate, which are all real numbers. But now I am saying I have an object which can be resolved along two axes. It should remind you of something like a plane, but these coefficients along these two axes can actually be complex. That's what one means essentially by a complex linear vector space. So this immediately means that the state of a quantum bit, if I assume that it's a vector, is not just about a pair of states, right? Because every point in this room is an element of this three-dimensional real vector space. It's not just the x, y, and z unit vectors, right? Every vector can be written as a combination of these three, and that's another element of the same space, right? So in the same way, if I'm thinking of the quantum bit no longer as just 0 or 1 binary valued object, but as a vector, then it means that first of all I can no longer like put a number to how many vectors, such vectors I have. I hope you understand that, because every object which can be written as a linear combination of these two is also an element of the same space, right? That is what one means by a linear vector space, a collection of objects which are closed under this kind of addition and scalar multiplication. So that is what leads me to this kind of a description. So the quantum bit is an element of a vector space, right, which is a collection of objects with certain rules of addition and scalar multiplication, right? Much like your real 3D vector space, you know how to add vectors, you know how to scale them by adding scalars, you know how to make projections along 3 orthogonal axes, and you know that every vector can be resolved in terms of a basis, which is a set of 3 orthogonal axes. So in the same way, any element, any object which can be written as a linear combination of these two basic states 0 and 1, two basic vectors 0 and 1, except that these coefficients can now be complex. So this is what an arbitrary state of a qubit can be. A bit is only in one of two states, 0 or 1, but a qubit is any complex linear combination of two states 0 and 1, where these two states are to be thought of like a pair of orthogonal directions in some abstract vector space, not necessarily associated with a real three-dimensional space, right? So this A and B, I said, are complex numbers. However, I want a physical realization of this. What I described is a mathematical object. Mathematically, this is something called C2. I think I write this on the slide as well, but this is something that's called C2. That is a complex linear vector space. It's a two-dimensional complex linear vector space, right? That is what a qubit lives inside. But physically, how do I realize such an object? So it turns out that the quantum states of a two-dimensional quantum system or a two-level quantum system exactly live in this space. So there's a deep connection between the states of a quantum system and these kind of linear vector spaces, specifically Hilbert spaces, a special kind of linear vector space. But for these finite dimensions, the distinction doesn't quite matter. So quantum mechanics says that states of a quantum system are vectors in a linear vector space. So in the same way, now I'm looking at states of a two-level quantum system, and it turns out that they are states in this kind of two-dimensional complex linear vector space. But now quantum states need to satisfy certain constraints, and one important constraint has to do with the length of the vector, the length of the state. The state has to be normalized, which then means that these two complex coefficients modulus squared has to be 1. So this is not a mathematical constraint, this is a physical constraint that comes from having these objects actually be states of a quantum mechanical system. So this is what a quantum bit is. It belongs to, like I said, a two-dimensional complex linear vector space. Now I can make this a bit more concrete, and then I can actually give a matrix representation for these objects. So this is what is called a ket 0 and a ket 1. This is the famous Dirac notation introduced by Dirac to represent states of a quantum system. And of course, the fact that you can make these kets and their adjoint objects are called bras, and then you make brackets and so on, it simplifies a lot of the algebra that you do on these linear vector spaces. But we're not going to do much of that in today's talk, but I just want to show this notation because no literature or paper on quantum computing can be read without this notation. So this is the so-called bracket notation of Dirac. It just means that this, or whatever this object is a vector in a vector space. In this particular case, it's a two-dimensional vector space. Now, how do you assign dimensionality to a vector space? You assign based on how many linearly independent directions you have in the vector space. So in this case, you have two linearly independent directions, specifically actually two orthogonal directions, and one of them is this ket 0, the other is this ket 1. Now, we can give a more concrete representation to this, because now I also want to talk about taking dot products or inner products of these vectors. Just like how in three-dimensional real vectors, I talk about things being orthogonal based on a notion of a dot product, right? In the same way here, I would like to define an inner product so that I can talk about these abstract objects being orthogonal. So in this case, I can make this a little bit more concrete by visualizing this vector space as a set of matrices like this. So these are essentially 2 cross 1 matrices. These are sometimes called column vectors because they're essentially single column, right? And you can see that if I assume these two to be some elementary column vectors, 1, 0 and 0, 1, then every column vector of the form AB can be written as a linear combination of these two things. So this entire set forms a vector space, and now I can define these inner products and so on simply via matrix multiplication. So what is an inner product? It is something that takes two vectors and gives me a scalar out of it. So how do I take two matrices, all of which are of this column type, 2 cross 1, and get a number out of it? I can't just do it with column vectors. So if I want to take an inner product, what I do is I make one of them into a row vector. So what is a 2 cross 1 will become a 1 cross 2, and then when I take a product between a 1 cross 2 and a 2 cross 1, I end up with a number, a 1 cross 1 object, right? So that is how I define the rules of this vector space now. So this gives a more concrete visualization for this states of the qubit. I can now think of them as these kind of two-dimensional column vectors, and all such vectors AB, where A and B can be complex, can now be written as some linear combination of a pair of basic vectors. These are called bases states, or this is, for example, one basis for this vector space. It's essentially a pair of orthogonal states. In this case, they are also even normalized. Normalized just means that if I take the inner product of this with itself, it is 1. I don't think I've written down the inner product on the slide, so if you want. So how do I define an inner product? So I take this ket 0 and I convert it into its adjoint or its dual, and that is what we call a bra vector. So this is a ket and this is a bra. If this has a representation of this form, this one, the dual, says you take the transpose of this and the complex conjugate. In this case, there is no complex conjugate, so it's just the transpose of this. So this is basically 1, 0 transpose. And then I can stack up these two things together like this, right? So, this was 1, 0 and this was 0, 1, right? So this is 1 and this is the same as the ket, but it is now the dual ket or the adjoint ket, which we call the bra. So this is the bra and this is the ket, and you see the name, it's bra ket. So anyway, so now you just do matrix multiplication. So this is a 1 cross 2, this is 2 cross 1, and this just gives me 0. It gives me a 1 cross 1 object on a scalar, right? And this is what I mean by an inner product, and this is what I mean by orthogonality. So when I take two such vectors and I take this inner product, if I get 0, they are orthogonal. If I take the same vector and I get 1, then I say that it has length 1, it's normalized, etc. So this is a general qubit state. Now it's a element of this two-dimensional vector space with a specific representation in terms of these kind of column matrices. Physically, what is it? It's a two-level quantum system. So I want to give you an example of such a two-level quantum system which can act as a qubit. So the simplest example of a quantum bit is actually the so-called polarization states of light. Any questions so far? Everyone's familiar with vector space and so on? Yeah? Okay, fine. So polarization states of light. So what do I mean by polarization states? So you all know that light is a what? What kind of object is it?
EM wave.
It's an EM wave. What kind of EM wave? Transverse. That's what I'm getting to because I'm talking about polarization. What does that mean?
E and B are perpendicular.
Right. So the plane of oscillation of E and B is perpendicular to the direction of propagation. So now I'm assuming that the direction of propagation is coming out of the plane of the screen. So then my electric and magnetic fields can oscillate in any which way within this plane, right? And if I fix one, the other is fixed by Maxwell's equations. So let's say we fix the direction of the oscillation of the electric field perhaps. And now you see that I could have different kinds of polarization. So polarization essentially refers to the direction of oscillation or the vector, the oscillation, the vector that describes your electric field. So in this case, let's say the electric field is, so the plane that's coming out is the z-axis, let's say. Then this could be the x-axis. So I could have the electric field purely being along the x-axis. I could have it being purely along the y-axis. So this would be called vertical polarization. This would be called horizontal polarization. But I could also have a 45 degree polarized. I could have 135 degree polarized and so on and so forth. So I could have a whole set of polarization directions in this plane, right? So this is all what we discussed. And now I assign this state 0 and state 1 of the qubit to specifically the vertically polarized light and the horizontally polarized light. But now I don't just say vertically polarized light, I say a single photon state. I say a single photon state which is vertically polarized. I call it the 0 state of the qubit, and the single photon state which is horizontally polarized, I call it the 1 state of a qubit. And one can show that the mathematics of a two-dimensional complex linear vector space is exactly what is satisfied by these kind of states of polarization of light, because they also live inside a complex linear vector space. There's a complex phase that comes in because it's a complex, there's a phase degree of freedom. So essentially whatever we said about two-dimensional complex linear vector spaces can be mapped exactly to polarization states of light, except that when you're talking in this kind of a bulk picture where you have many photons like light that comes out of a laser and so on, which could have specific polarization, but when you have tons of photons there, that's not really a single quantum state. What you're talking about as a single qubit state is really a single photon carrying a specific polarization state, right? So this was in fact the earliest physical realization of a qubit, sometime in the mid-80s again in IBM Yorktown Heights lab. So let's get into this polarization qubit a little bit more. So things that we spoke about like orthogonality have very physical manifestation here, right? When I say that the 0 and the 1 state are orthogonal in the mathematical sense by taking an inner product in the vector space and so on, physically it has a certain meaning. So what is the physical meaning of this? It means something very simple which we use all the time in things like Polaroid glasses and so on. It means simply that if I put a horizontal polarizer or a filter that's going to filter only and allow only horizontal polarization through, it will not allow vertical polarized light through. And this kind of a polarizer can only be made for axes which are perpendicular in some sense and which correspond in the qubit sense to states being mutually orthogonal. So conversely, if I prepare a vertical polarized filter, it's not good. However, now you have also non-orthogonal states, because if I now prepare a 45 degree polarizer, one that is only going to allow light of this kind through, you realize that if I shine vertically polarized light on it, will it go through or not go through? Sorry? It will partially go through. Half of what? Half the intensity. Very nice. Yes, exactly. So now you realize that if this is the axis of the polarizer or the filter, then if I shine vertically polarized light, also there's something that's going to go through. If I shine horizontally polarized light, also there's something that's going to go through. So this is now an example of states being mutually non-orthogonal in the quantum sense. Okay? It means that this state and this state, when I write down, there is a certain overlap in the inner product sense. But now the question is, instead of shining a laser light which is vertically polarized, what if I send a single photon which is vertically polarized through this 45 degree polarizer? What happens? Now there's no half intensity. You can't split a photon. So what happens? What happens if I send a single vertically polarized photon through this?
It's like half probability.
Yeah. So now the probability element comes in. So now you have a certain probability of seeing the photon after this 45 degree polarizer and a certain probability of not seeing the photon. Now where does that, how do you decide that probability? You write down the state of this photon, you resolve it along the 45 degree axis and an axis that is perpendicular to that. You can't simply say there's so much projection along this, you have to resolve it along a pair of orthogonal directions. So this now is essentially like performing a quantum measurement. You have to take a set, in this case a pair of orthogonal states, and that is what gives us a basis in which to perform a measurement in. So the act of sending a photon through a particular polarizer is as if you are now measuring along this and its perpendicular axis, which is a 135-degree line, you are measuring whatever state you're sending in. Suppose you send exactly 45-degree polarized light. What's going to happen? Single photon 45-degree polarized through this polarizer is going to always come out with probability 1. If you had a single photon which is 135-degree polarized through this polarizer, what happens? Never comes out. Probability 0 of coming out. Either of these have probability half. So now you realize that this idea that one is talking about, which is writing things as linear combination. So now what I'm saying is you can write this state, for example, as a linear combination of this and this. Right? How would you write this as a linear combination of this and this? Just cos and sine, 45. So that's 1 over root 2, 1 over root 2. And now you see where the half is coming from. So these coefficients of writing this in terms of this and this, those coefficients, which I wrote down there, A and B, right? The modulus A squared and the modulus B squared. Remember I said that should sum to 1. The reason it should sum to 1 is because modulus A squared essentially represents the probability of the qubit being in the state 0. The modulus B squared represents the probability of the qubit being in the state 1. And so together, if this is to make a complete experiment, then you need these probabilities to sum to 1. So that is where this constraint of mod A squared plus mod B squared comes about. Okay. So this, using the polarization qubit, you can really understand a lot about two-level quantum systems. So what I explained is the fact that some states are going to be mutually orthogonal and they form a basis for measurement. But of course, there are non-orthogonal states. And now you can write down these states. So this is the 45-degree polarized state in terms of the 0 and the 1. Remember, for me 0 was vertical, 1 was horizontal polarized. Of course, that's a matter of convention. That's my notation or convention that I have picked. You could decide to use 45 polarized as ket 0, in which case everything would change. The 135 would be ket 1. The vertical polarized would be a superposition of this form. The horizontal polarized would be another superposition of this form. In my notation, the 45-degree polarized, right, this is what we call a superposition, right? A linear combination of the 0 and the 1 state with these coefficients being 1 over root 2. The modulus squared of this coefficient is what gives me the probability of measuring this state in either 0 or 1. Now this is a particularly useful state, so we call it a plus state. This I can define for any two-level quantum system. In this particular case, I have defined it for polarization. I could instead have repeated the whole thing with a spin-half particle, for example, which can exist in one of two spin states, a plus or a minus, in the presence of an external magnetic field. And then all of this I can again repeat for a spin-half particle, right? Or any such physical realization of a qubit. The 135 polarized is, of course, has now a relative minus sign. So you see that, of course, here it's not complex, but of course I could also put an I here and make this complex, and that would represent a different state. So you see that this relative sign between the 0 and the 1 becomes important. It actually corresponds to a completely different physical state, in fact one that is even mutually orthogonal to this. So you can do the same inner product math that I did here between these two states, and you can show that it's a pair of orthogonal states, right? Okay, so moving on. Now I can come up with whatever machinery that I have defined so far. I can come up with a nice geometric description of the qubit, and that's what I'm going to do. So I'm being more formal now. A qubit is a normalized complex linear superposition of this form. I explained most of the terms here. But now I can parameterize this in an interesting way. I said mod A squared and mod B squared are probabilities. That is why they must sum to 1. Okay. But now I have these two things which sum to 1. This should remind me of cosine and sine. So indeed I can now replace, and so what I can now do is, this is just the amplitude of a complex number, and I can represent every complex number in terms of an amplitude and a phase. But this is a pair of amplitudes which has to sum to 1. So these amplitudes must therefore correspond to sine and cosine functions of some angle, right? And what I need also is a complex phase. But you see, if I were to stare at this very naively, it's a pair of complex numbers. So if I start asking this question, how many real parameters do I need? to describe the state of a qubit, the naive answer would be 4, right? Because it's a pair of complex numbers. Each has an amplitude and a phase. So it should be 4, but I've already put this constraint on the amplitudes, so maybe 3. However, it turns out that you need only 2 real numbers to parameterize the state of a qubit. So what have I done here? I'm supposed to have one complex phase associated with this complex number A, and I'm supposed to have another phase associated with this complex number B. But I have only put one phase here. Why is that? What have I done?
You will factor out the.
I have taken out some part of the phase. So what is sitting here is actually the difference of those two absolute phases. So this is what we call a relative phase. But what happened to this overall phase factor outside?
You can drop it.
Why can we drop it?
Because it won't affect.
It won't affect what? Correct. Sorry?
The observation.
Very nice. Yeah, it won't affect your observations because probabilities are what you get finally. So what do I expect to see from a quantum state? Now a quantum state, unlike a classical state, is not something that comes with fixed predetermined values, right? Because to begin with, I've said it's a vector in a vector space, which means it is some linear combination of many orthogonal possibilities, and a measurement, like I said, is about collapsing it to one of these orthogonal possibilities. So it's essentially like saying I have a point here. If I want to measure it, what I'm asking is what is its x coordinate, what is its y coordinate, what is its z coordinate. So I'm taking projections along 3 orthogonal axes. In the case of this kind of abstract object, if I have an arbitrary qubit state and I want to measure it, I need to have a pair of orthogonal directions. Like I need to have vertical, horizontal filters. I need to have 45, 135 degree filters in order to read out the state. And what I'm asking then is how much probability does it have, how much weight does it have on each of these perpendicular axes. So it is one of many possibilities that I expect to get, but that doesn't for me tell me exactly what psi is, right? What it gives me is statistics, it gives me probabilities. So let's go back to this polarization example. So now let's say I do this test, I make this 45 degree polarized light, right? But I don't tell you that it is 45 degree polarized light, and I send you a bunch of photons with some specific polarization, and your task is to find out what is this polarization. So how will you set up this experiment? What will you do? You will have to start using polarizers of specific axes, specific angles, specific directions. And now, obviously with a single photon, I hope you see that you can't get any information out. You put a horizontal polarizer, you will get with some probability the photon out. You put a vertical polarizer, you will get the photon out with some probability. That doesn't tell you anything. You put a 45, 1, it's a single photon, you can't even estimate that this probability is 1, for example. So there's no way for you to actually even know that it's a 45 degree polarized photon that I have sent you. So you first of all need many copies of the same photon. You need me to prepare many copies of the same state and send you that. Okay. Now let's say you perform an experiment where you have vertical and horizontal polarizers, and you repeat this experiment many times, and let's say you gather the statistics, and then you find experimentally that the probability of this photon passing through a horizontal polarizer is half, that half the photons pass through the horizontal polarizer, half the photons pass through a vertical polarizer. You put that together and you realize that okay, maybe it is an equal superposition of horizontal and vertical polarizers. But still, you don't know the answer to whether it was 45 or 135 polarized, because both of them are equal superpositions of horizontal and vertical polarized, because the modulus squared is the same. So what I'm trying to get at is what you get out of experiments is the modulus squared of this thing. So now whether or not I have an overall phase here is not going to affect these probabilities. But let's go back. If my claim is that relative phase matters, then how can I get the relative phase out of this experiment? So what you need to do now is I should not only send you 1000 copies and say 500 times you get this and that. You ask me to send another 1000 copies, and now you rotate your polarizer. You have now guessed, let's say, that it is either 45 or 135 degree polarized. But now you have to rotate and measure in a different basis. You have to now measure using a 45-135 filter, and then you know for sure, this thing never passes through the 135 polarizer or filter, so it must be 45-degree polarized photon. So it's not only about measurement in one basis, you need to measure in multiple bases, collect statistics in order for you to completely reconstruct the state. But the point is that this relative phase is something that can be identified, can be measured, can be distinguished, but whether or not I have an overall plus sign or a minus sign here is not something that can be measured experimentally. So in quantum mechanical terms, we say that this overall phase that should have been here is not a physical observable. There is no experiment that can actually reveal that overall phase to you. All quantum states are the same up to an overall phase. What matters is the relative phase, and this relative phase is what I have parameterized by an angle here, phi. So this phi is something that goes from 0 to 2 pi. This amplitude is parameterized by another single angle theta. I've made it a half angle for a reason. And this theta goes from 0 to pi. Now what do these two angles remind you of? Polar coordinates. So what is the geometry that they remind you of? A sphere. So this actually should remind you of the surface of a sphere, a unit sphere, in real three-dimensional space. So now I've made a connection between the states of a qubit and points on the surface of a sphere, and this is the famous Bloch Poincare sphere. It's a geometric visualization of a quantum bit. This kind of mapping exists only for two-dimensional quantum systems, in the sense of having this exact one-to-one mapping between the points on the surface of a sphere and the states of a qubit. So now I can sort of draw the sphere and I can identify. So let me go back and say, the way I have written this now, theta is for me the angle that I make here, this polar angle, and then I drop a, so it depends how you define your axis. So this is my z axis, what's coming out now is x, this is y. Theta is the angle that I'm making with the z axis here, and then I drop a point to the xy plane, that's an equatorial plane here, and then whatever angle I make with the x-axis, that's my phi. It's the usual spherical polar coordinates way of writing things. So now you realize that when theta is 0, I have the 0 state. When theta is pi is when I have the 1 state, right? So the 0 state is at the north pole, the 1 state is at the south pole, and then you have all possible points on the surface of the sphere. So this gives you a very geometric feel for why one might want to think about quantum states as information storing objects or units of computing. Because while the classical bit has exactly 2 points to explore on the surface of the sphere, the quantum bit has this the entire surface of the sphere that it can explore. So what you think of as your state space or your computational space has just exploded now. Because it's not just these 2 points, but it's everything on the surface of the sphere. You can of course identify special states. You can identify the 45, 135 states here. Now you can put a complex phase here, right? And those are the 2 states here, and so on and so forth. So this is a nice way to picture the qubit. And if you go today and log into, let's say, the IBM quantum processors, I suppose you all know that everyone has access to go and log into these quantum devices on the cloud. If you actually do that, and you can sort of manipulate states and so on, they'll show you, like, you can kind of drag and drop and you'll see the state moving around on the Bloch sphere. Okay? Questions? Right, so what I've identified here are essentially 3 different ways to view the qubit, or 3 different measurement bases for the qubit. So the normal one that we spoke about was a 0 and 1. This is like putting horizontal vertical filters. If resolving it along this axis, which we call plus minus, is like doing the 45, 135 measurement. You can also resolve it along the 3rd axis, and this is how you would, for example, estimate if there is a complex phase here, true, right? So it turns out that if I pick some arbitrary point here and I say identify for me the state of the qubit, means identify for me the theta and the phi, right? And in order to do that, you need to perform not just 1 measurement, not 2 measurements, but actually all 3 measurements in order to reconstruct the state fully. So this is a set of 3 orthonormal bases for the qubit. For those of you who are interested in structures in linear vector spaces and so on, these 3 bases have an interesting structure. you realize that if I were to take this basis and ask what is the probability of getting the states in this basis, you see that it is equal. If you were to take this basis and ask what is the probability of getting the states in this basis, you can work out again. The probability, remember, is just have to take the overlap and the modulus squared. I have to take the inner product and I have to do a modulus squared. So you realize that that is also equal. So if I am in one of these bases and I ask what is the probability of getting one of these two outcomes or one of these two outcomes, it's all equal. So this is what we call a set of mutually unbiased bases. Because essentially it's like tossing an unbiased coin, right? If this is my head and tail and I have these states and I ask what's the probability of getting head and tail, it's equal. If this is head and tail, it's the same way, it's equal. So this is a set of 3 mutually unbiased bases, and there is a theorem that actually tells you how many such mutually unbiased bases can I have in a vector space of a particular dimension, and it turns out that 3 is the maximum that you can have in a 2-dimensional vector space. Quantum mechanically, the connection is that it suffices, so you can ask why only these 3? Initially you told me you measure in 0, 1 basis, that is horizontal, vertical. But then you said, oh, but you can't distinguish between plus and minus if you do that. So you measure in 45, 135. Now I'm telling you that you need a 3rd basis. So what's preventing me from stacking up more and more such directions? So there's an infinity of such directions that I can pick, which correspond to pairs of orthogonal states. The point is, there is such a notion of informationally complete measurements. So it turns out that if I measure in 3 mutually unbiased bases, that is sufficient to reconstruct the state. And there is a deep connection between the number of such bases and this sort of notion of information completeness from a quantum mechanical point of view. Anyway, that's a sidetrack for people who are interested. You can go read up about mutually unbiased bases. But now I want to highlight another aspect of quantum theory, which again comes out simply with this polarization experiments. So I'm just formally defining what a polarizer is. I guess we all kind of understand what polarizers are. So what do I mean by unpolarized light? I mean that light of this kind, where it is not that every photon that is coming out has a very specific polarization. These photons are scrambled. They exist in all possible polarizations. But now if I pass all of this through a particular polarizer, it all becomes aligned along with some axes, and now I get specifically vertically polarized light or horizontally polarized light and so on, right? Okay. So now I can sort of formalize it like this. So I call an object a Z polarizer if it polarizes something along Z. So now I'm talking Z and X with reference to this sphere, right? So this is Z, this is X, okay? And I call something X polarizer if everything that comes out of it is specifically polarized along X, okay? Now what I want to do is to start stacking things up like this in sequences of polarizers. So if I have a Z polarizer, I first have, let's say, unpolarized light, and I have a Z polarizer, then what comes out is all Z polarized light. If I now put another Z polarizer, what's going to come out is again Z polarized light. But now if I put X polarized light, what happens? Nothing comes out. I'm sorry, if I put an X polarizer here, nothing comes out, because this is now oh, I'm sorry. Yeah, I didn't mean Z and X in that sense. Okay. So, yeah, as far as these slides are concerned, Z means vertically polarized. Sorry. So, sorry. So, Z is vertically polarized and X means horizontally polarized. Okay. So, that's what I wanted to say here. So, together with Z and X, I get a complete basis. Okay. Have I confused you completely, or let me just write down what I mean by this. So we've spoken about vertically polarized light, and this is what I will call Z polarized, at least for these two slides. And this is what I will call X polarized light. Okay. So together, this gives me this pair of orthogonal states for a qubit, right? Now when I say pi by 4 polarized, that is what I mean by 45 degree polarized, right? So this is this so-called plus or minus state where I could have this equal superposition with a plus or minus in between. Okay? So this is my notation for these two slides, but I am trying to convey an important physical principle here, so maybe just pay attention. So what I'm trying to say is if I had a Z polarizer and I shine vertically polarized light or Z polarized light on it, I expect to get the light with full intensity, but if I instead place an X polarizer, I get nothing out of it. This is something we already discussed, right? You told me probability is 0 and all that. Now all I'm pointing out is that if I in between, so in doing this experiment, if in between I had put a pi over 4 polarizer, which means this kind of 45 degree polarizer, that changes the outcome of this experiment. Because initially, because it was vertically polarized and I put a horizontal polarizer, nothing comes out. But in the middle, if I put a 45 degree polarizer, something does come out. So what has happened in this sequence? If you think about it, this Z together with X, like I said, is like measuring in this orthonormal basis. So I have projected all the light onto this orthonormal basis. But in the middle now, I have projected onto a different orthonormal basis, which is the 45-135 basis. So by putting in a measurement along a different basis, I have actually changed the outcome out here. With polarizers, it seems something completely trivial because of course, yeah, if I put 45 polarizer, yeah, you will end up now having some component. So what's happening? Some component of the vertical polarizer passes through this because this is 45 degree polarized, and then some component of 45 degree polarized is going to pass through the X polarizer because this is now horizontally polarized. The nice thing is that if you now do this at the single photon level and you do this over many shots and you collect some statistics out of it, this actually is a manifestation of the so-called uncertainty principle. Because what does it say? It says that I started with a particular state. Do I have that slide here? Okay. I don't have it. So maybe I'll just show you what I wanted to convey through that sequence and why it is connected to the uncertainty principle. So I started with something which is vertically polarized. I put a particular box here. This box I'll call a measurement box, which measures in this 0-1 basis. So the vertically polarized was 0. This is a 0-1 basis measurement. I start with 0, so I expect to continue to get 0 out here, right? Now, if instead I put, so this is the meaning of putting a Z or an X polarizer here, right? But instead if I put a 45 degree polarizer, then what happens? I have two possibilities. I could either have 45 degree polarized light, which is maybe plus state, or I could have 135 degree polarized light. And now, so this was the quantum state of the single photon here. I did a measurement here of this kind. Now if I take this and do a measurement, I do another measurement, this time in the same 0-1 basis, right? Whereas earlier, this measurement had a fixed outcome. It was only 0 because the state that was prepared was 0. I could never get a 1 outcome here. That's equivalent to saying that if I put an X polarizer, I always get 0 out, right? But now, by putting the same measurement, I can get either of these two outcomes, and what is more, both are equally likely. So long as I am measuring in this basis, I have complete information about the state. Meaning with probability 1, I know what the state is. That's what I mean by complete information. I have no uncertainty about the state. But by putting in some intervening measurement in a different basis, I have actually changed this probability distribution. It was a delta distribution, 1-0, which has now become a uniform distribution, half-half. So from a 0 entropy state, I have actually gone to a maximal entropy state because what I tried to do in between was to measure in a different basis. So what this tells you is you cannot hope to have accurate information simultaneously about both this basis and this basis. Either you know that the light is horizontal vertical polarized, or you know that it is 45-135 polarized. If you try to take this state and measure it in this state and go back and measure in this basis, you're not going to get the same measurement result. If I continued measuring in this basis, nothing changes. But once I put an intervening measurement in a different basis, it has actually changed the distribution of the state. So this is one manifestation of this uncertainty principle, which we've all seen in the case or heard about it in the case of position and momentum, right? Because you say that you cannot simultaneously get position and momentum with accuracy. That's one version of the Heisenberg uncertainty principle that's commonly stated and taught. But here I'm showing the same kind of uncertainty principle for you for a very simple pair of observables, namely the polarization state of light, where the observables in question are horizontal vertical versus 135-45 degree polarization. And these two measurements, this pair of measurements is not compatible with each other. If I make one measurement, I lose information about the state in the other basis and vice versa. So such incompatible measurements are called complementary properties of a system, and I kind of explain the whole thing again on the slide. Mathematically, of course, it means that I have matrices associated with them which are non-commuting. That is where the term incompatible comes from. Those of you who know some quantum mechanics know all the connection. The one final thing I want to point out is that this uncertainty principle has nothing to do with the limitations of the physical apparatus that you have built to do the measurement. It is a mathematical, it's a deeply mathematical property, right? Once you have defined a mathematical structure for your quantum state space, which is the state space of linear algebra, which is this linear vector space, finite dimensional linear vector space, etc., then it's a property of the states and the observables that there are observables that will not commute, that will be incompatible or complementary in the sense, which will satisfy an uncertainty principle, no matter what kind of precision measurement that you physically, apparatus that you physically build, right? So it's more a statistical statement, because it's saying that it is statistically impossible for you to get information simultaneously in multiple bases, and the physical manifestation of that. So in particular, position and momentum are two such observables, and that's why we commonly state. But unfortunately, many times when it is taught in a sense as if, you know, if you made your microscope better, or if you made something better, you can, you know, it's spoken about as some kind of measurement error, but it's not measurement error. The bound that you talk about, the standard deviation, is a fundamental statistical property of these systems. Okay. Questions?
Can we go back to the Bloch sphere slide?
Yeah.
Yes, so here we only need to measure theta and phi to get the.
Yeah.
So like why do we need to measure in all three horizontal bases?
Yeah, so you can, yeah, so maybe the way to do it is to actually take the state, right, and write it down in terms of, I mean, just maybe write down your state in the 0-1 basis. Measure, so if you measure in the 0-1 basis, then what is the information that you get? So you go back. So if I measure the state in the 0-1 basis, then what is the information that I get? Probability of being in 0 or probability of being in 1. What is probability of being in 0? Cos squared theta by 2, sin squared theta by 2. So this is all the information that I get. Now here you will realize that it's e to the I phi, which means I have a cosine phi and a sine phi sitting here. So in order to actually extract that cosine phi and the sine phi, I will have to, so in a sense it's like real and imaginary parts of this phase degree of freedom, right? In order to get that out, I will have to measure in two other bases. So you can now ask, rewrite the state in the plus minus basis. So how do I rewrite in this basis? It's a linear transformation, right? So this is how, So I can use this to say that, how do I write 0 in terms of plus and minus? 0 is again plus plus minus over root 2, 1 is plus minus minus over root 2. So I can go back here and substitute and rewrite the same state in terms of plus and minus. And you can ask what are the two coefficients I will get. It turns out that in one case you will get the cosine phi alone, in the other case you will get the sine phi. Okay. One simple way to see it is, for example, the fact that if you had if I had a plus I and a minus I here, this measurement, the 45-135 measurement, is not going to distinguish between the two. You need a third measurement in order to get that plus I minus I resolution. Right? So one only tells you about the imaginary real part of the phase, and the other tells you about the imaginary part of that phase degree of freedom. Okay? Yeah. So you have to write the state in terms of the three bases, extract the statistics out, meaning what are the coefficients in each basis, right? Those coefficients will tell you the probability that you get, and that is what you can experimentally get, right? So in one experiment you only get theta, which is the Z experiment, the 0-1 experiment. You get cos squared and sin squared theta, from which you can get theta. In the other experiment, you don't get phi in one experiment. That's what I'm trying to say. You get either sin phi or cosine phi, but that's not enough for you to fix this phase complete. Okay. Questions? Yeah.
Would there be quantum states inside the Bloch field?
Yes, there are. Good. So all of these were length 1 objects, right? And all of these things on the surface of the sphere can be written as some linear combination of 0 and 1. That we know. What is inside the sphere? So for example, if I had a point here, let's say on the z-axis, think geometrically, this point is 0, this point is 1. What would a point here be? If in a geometric situation, what would it be? I have some line segment. This represents something, this represents something. What would be some point here?
Like 0 scaled down.
Not just that, right? It means that I have some, I don't know if people have heard the word convex combination.
Yes, linear combination.
Yeah, except it is I'm going to say convex combination of this and this. Okay? However, you realize that this point cannot be a superposition of this form. Okay? And also its length is no longer 1. So something has happened where you have shrunk the length of this thing, but then it's some combination of 0 and 1. So what is inside is what we call mixed states. So what do I mean by a mixture? So I'll give you one example of this, very simple. So we go back to so you see everything I explained in terms of my 0-1 polarization experiment. So let's say I prepared 45-degree polarized light, many photons, okay? And I do this measurement. I know what I'm supposed to get. With probability half, I get 0. With probability half, I get 1. I repeat this experiment many times. What do I end up with at the output? I end up with a collection of states which are half the time 0 and half the time 1. How do I mathematically represent this outcome? Can I represent it again as a superposition like this? Can I? I can't, because I either have 0 or I have 1. If I track a single experiment, I either have 0 or I have 1. So a single experiment is a collapse. This is the famous Von-Neumann collapse postulate, that when you measure, you collapse onto one of a set of orthogonal states. But if I want to represent this ensemble, this collection, if I want to represent this complete statistical object that I have here, then what I have here is actually a statistical mixture. It's a mixture of 0 and 1. So it is like I have this collection of states 0, 0, 1, 0, 1, etc. Right? Where finally, if I take a look at this full collection of states, half of them will be 0 and half of them will be 1. But there is no interference or there is no connection between the outcome of these different experiments. Each of them is an independent trial. It's like looking at the outcome of a set of 1,000 coin tosses. There is no connection between one coin toss being head and the next one being a tail. They're independent events. So it's the outcome of a bunch of independent events. And this outcome is a statistical mixture of 0 and 1. Mathematically, the way to represent it, it turns out, is in terms of what is called a density matrix. How many of you have heard of density matrix? Oh, okay. In what context have you heard of density matrix?
Yes, sir.
Okay, so this is all familiar stuff to most of you. But, so in quantum mechanics, you've heard of density matrices. So, okay. So how would you represent this then? Why is it a matrix?
Well, it's 0 and 1 are classical bits, right?
Sorry?
0 and 1 are classical bits if you just consider the points of the line.
Why the classical bits? I didn't understand.
No, like if you just consider the point of on the vertical line without going outside the sphere. Like the outside of the sphere is a curve, right? So that is the 0 plus 1 normal, what we use in quantum bits, right?
No.
Outside of this one.
The surface you mean? Okay,
yes.
outside of the surface. Okay, sorry. Yeah. Okay.
Right?
Yeah.
0 plus 1.
Okay.
So if you go inside, it's a combination of either zeros or ones, which lands on the line which is the classical bit.
Okay, but I'm asking, is there a mathematical description of it beyond this geometric line? I'm saying, why is it called a density matrix? That's what I was asking specifically. Why is it a matrix? So, it's a matrix because the way you finally represent the state is in terms of projectors. You represent the final state in terms of a projector on 0 or a projector on 1. And what is a projector? A projector is a mathematical operator, right? And it's a mathematical operator that collapses you to either 0 or 1. So if it's a projector on 0, it collapses you to 0. If it's a projector on 1, it collapses you to 1. So since you say that you're familiar with everything else, let me give you something that maybe you have not seen, I don't know. It's very hard for me to gauge the level of this audience. So if something is extremely familiar to you, you can please tell me to move on. But this is what I would call a projector on 0. This is a projector on 1. Why is it a projector? So this is a different object from this kind of an object that I wrote. This is an object I showed you. It takes a vector, it takes the transpose, it makes it a row vector, and it gives you a number out of it. This is an object where you've taken the vector, you've taken the dual of the vector here. So while this is a 2 cross 1 object, this is a 1 cross 2 object. So what this finally is a 2 cross 2 object. So this is a matrix. And in specific, this is a matrix that projects onto 0. This is a matrix that projects onto 1. So the way to represent these points on this line is as a matrix of this form. I'll put half, but maybe just say. If it was this equal superposition, then it's this matrix. Otherwise, it's something like P plus 1 minus P, where depending on what P is, how close you are to 0, that's what your P is. Yeah? Sorry, is there something? Okay, so this is what is inside the sphere, and you can see that if P is a half, where are you actually? At the center of the sphere, and that is what you call a maximally mixed state, because it's an equal mixture of 0 and 1. And in fact, what one said at the very beginning about these quantum states being noisy is essentially this, that you go from being on the surface of the sphere to points in the interior of the sphere. Points on the surface of the sphere are called pure states because they actually represent coherent superpositions of these kind of basis states. But points on the interior are no longer superpositions because, like we said, the way to realize points in the interior is by doing processes like this. Now this is a measurement process. This is a process that actually breaks superposition because you started out as a superposition of 0 and 1 and you ended up with an ensemble of states where you are either 0 sometimes or 1 sometimes with no coherent connection between the two. So you had some phase information here. For example, I can do the same experiment with the minus state and I'll end up with the same ensemble. I can do the same experiment with that plus y, minus y states, and I get the same ensemble. So there are multiple states which after this measurement have mapped me to the same density matrix. So I have lost some information there. What is the information that I have lost? Between plus and minus I have lost whether it's a plus superposition or a minus superposition. I have lost the phase information, relative phase information here. So this is an example of what is called decoherence. So you've lost this information about the superposition. By moving into the interior of the sphere, in this particular case, you have mapped all points to the center of the sphere. You measure 0, 1, you go to the center of the sphere. You measure plus, minus, you go to the center of the sphere. That is, if you don't keep track of each outcome, if you look at this as an ensemble. So it turns out that there are processes like this that happen naturally in a quantum system that is not closed or isolated. So an open quantum system, I'm now throwing jargon at you, is something where this kind of decoherence happens and you get mapped from points on the surface of the sphere to points in the interior of the sphere. So you go from pure states to these kind of mixed quantum states, and this process is called decoherence, and that's what makes today's quantum processors noisy. That was a very long answer for what's in the inside of the sphere. Yeah.
Are there states outside the sphere?
No. This is the entire state space, including points in the inside, that captures all possible quantum states of a two-dimensional quantum system or a two-level quantum system. Yeah.
Well, even for the states inside the sphere, you will need 3 spaces in between.
I will need 3 basis measurements. Is that what you're asking?
No, like the basis will be consist of 3 vectors.
Basis is a pair of vectors, but I will need 3 such bases. Yeah. I will need 3 bases to completely reconstruct any state in the interior. Is that what you're asking? Yes. In fact, because, well, I said it's a matrix, it's a 2 cross 2 matrix. It's a 2 cross 2 matrix with certain properties. It will turn out to be a trace 1 Hermitian positive, actually not just Hermitian, it will be a positive trace 1 2 cross 2 matrix. Once again, you can ask how many real numbers do I need to describe a positive 2 cross 2 trace 1 matrix, and you will wind up with 3. And it will turn out that those 3 numbers essentially correspond to measurement outcomes along these 3 different bases. Okay. Other questions?
Is it because?
Yeah, go ahead.
Is it because that the other diagonal has 2 values and one of the diagonals has a significant because the other one is 1 minus the other?
Exactly. Each measurement only gives you one number because it's a 2-dimensional probability vector, which is just one real number.
No, I'm saying the density matrix 4 numbers, right?
Yes, but then you can work that out. But it's not just for 2 cross 2, so you can work this out generally for a d cross d. How many do you need? Yeah, indeed. So your off diagonals, one has to be complex conjugate of the other if it's Hermitian, right? So that's just 2 real numbers, and what's on the diagonal is one other real number because the trace is constrained to be 1. Yeah. Okay. Yeah.
Like this is like if you have like a lot of experiments and we get a collection of quantum states, a way to represent that is like a mixed state or a density matrix. But like if you think like the naive way to like represent something would be like a distribution over the like all possible quantum states, right? How can you like boil an entire distribution out like a matrix?
Yeah, so, so this whole representation of how you get this density matrix essentially comes from wanting to have a mathematical description of the measurement process itself. Okay, so if I want to, maybe let me move on a little bit and I'll come back to your question in the end, because this has to do with how do I mathematically model this transformation. So far I've only spoken about the quantum state space. I've said nothing about how states change, right? So let me talk a little bit about how states change and then we'll come back to this, because measurement will not fit into that. Okay? Obviously I'm not going to go through much, but I thought I should at least tell you a little bit about how you can use these objects for computing. And I really like this quote from David Deutsch, which says that computers are physical objects and what they can and cannot do is determined by the laws of physics and not just by pure mathematics. Okay, so what can you do with these quantum states? How can you transform them? Because if I want to use them for computation or information processing, it means that I have to change them in some way. So how do they change, right? classically, how do I compute? I use these kind of gates, right? So this is a single bit gate. So what kind of single qubit gates can I construct? So can I construct the analog of this thing where 0 goes to 1 and 1 goes to 0? Of course I can construct, but now is where the matrices start coming in. So this is why I said let me answer this question after I've spoken about these kind of things. Now what am I asking? I'm asking you to transform one column vector into another column vector. So I'm asking you to transform vectors essentially. So what kind of object can do that? Another matrix can do that, right? So I need matrices as quantum gates in order to transform vectors which are quantum states. So what is an example of such a matrix? So I need 0 to go to 1, 1 to go to 0, but more importantly, I need any superposition of 0 and 1 to also transform in the same way, meaning a vector AB should go to BA. So here is an example of a matrix that can do that. So this is what is called the quantum X gate. This happens to be one of the Pauli matrices that you may have seen. This is the Pauli X matrix, and this is a quantum NOT gate. So now you start realizing that okay, maybe all quantum gates are matrices because they have to transform vectors. Now the question is, can any matrix, in this case 2 by 2 since we are talking about 2 dimensions, can any 2 by 2 matrix be a quantum gate? The answer is no, because you also have to satisfy a constraint, which is that the length of these things has to be 1. So when I put in that constraint, then I realize that these matrices have to be what are called unitary matrices. So any unitary matrix can indeed be a quantum gate. So those of you who have done quantum mechanics know that, maybe you know that quantum states transform according to unitary matrices, right? So if I talk about how a quantum system evolves, I typically write down, I don't know how many of you have done quantum mechanics courses here, I typically write down a Hamiltonian associated with the system. I maybe solve Schrodinger equation, but the other way of doing it is to actually simply write down a unitary matrix that comes out of this Hamiltonian. And that unitary matrix will tell me how the state evolves with time. So that's exactly what one is saying here. So any unitary matrix can act as a gate that transforms quantum states. However, this kind of a picture applies only for closed quantum systems, that is isolated quantum systems. You pretend that this two-level system is all there is in the entire universe. There's nothing that is interacting with it. If I now put a bath or an environment that is interacting with this two-level system, then it turns out that this unitary picture actually breaks down. So this is an answer to your question. This unitary picture breaks down already when you look at measurement, because I cannot model this measurement as a unitary transformation. How do I model the process of plus going to 0, minus going to 0 with some probability, plus going to 1 with some probability, minus going to 1 with some probability? So this process can no longer be modeled as a unitary transformation. So measurement is something that lies outside the purview of the standard quantum mechanical, Hamiltonian, unitary evolution, Schrodinger equation picture that we know. If you want to model measurement, then you need to go out of this picture of having only pure states. You need to consider mixed states, and then you can expand the scope of your set of transformations from unitary to something beyond unitary, which allows you to describe going from a pure state to a mixed state. So that is why this notion of a mixed state was even introduced, to understand what is really happening to your state at an ensemble level, right? Okay. Right, so let's go back to computation now. So that was a single qubit gate. Now I can write down, in the classical case, you have only one single qubit gate. Okay, you have identity and then you have the NOT gate. But in the quantum case, you have the quantum NOT gate. But that's just one example of a 2 by 2 unitary matrix that I can write down. There are several 2 by 2 unitary matrices I can write down. For example, I can write down a simple diagonal matrix 1, 0, 0, minus 1. That's not an identity gate. That is a gate which takes 0 to 0, that is 0 to 0, 1 to minus 1. Classically, that's not even a non-trivial transformation, because there's no notion of minus 1. My state space is just 0 and 1. But now I have 0 going to 0, I can have 1 going to minus 1. So then I can have A plus B going to A minus B. So that is an example of a quantum gate which has no classical analog. So let me just write that down also. So that is an example of a quantum gate. So I can have a gate of this kind. This is also a unitary matrix. This takes something like AB to A minus, and this is a non-trivial transformation as far as quantum states are concerned. So this is a non-trivial transformation of my qubit. So this is what is called a phase flip gate, because I have flipped the relative phase between A and B. Now then you realize that there are indeed several single qubit quantum gates that one can write down which don't have a classical analog. So the quantum single qubit gate space is much richer than the classical single bit space, right? But going beyond that, I can't do a computation which is single qubit gates, I need multi-qubit gates. So classically we have several multi-qubit gates, right? And we know that these are so-called universal gates, which means I can write down all my any Boolean function as I can obtain it entirely in terms of just NAND, NOR or XOR, one of these universal gates. So quantumly, is there a similar analog of a universal gate set for quantum computing, for computing with these quantum bits? So it turns out that there is such a set, and it involves a very important 2-qubit gate called a controlled NOT gate. So this is in some sense a quantum analog of the XOR gate. So this is what the controlled NOT gate is. I have two qubits, X and Y. One of them plays the role of control, the other plays the role of a target. The control qubit remains unaffected. The target qubit changes depending on the state of the control. So now I have moved from talking about single qubits to multiple qubits. This is a 2-qubit register now. I'm drawing the simplest example of a quantum circuit. I'm writing down a gate here which involves both these qubits. It does nothing to the first qubit but changes the state of the second qubit depending on what the value of the first qubit is. So you can do this XOR operation. You realize that whenever the control qubit is 1, the target qubit gets flipped. So this is a NOT gate but with a control knob attached to it, and this is a basic example of a 2-qubit quantum gate. But there's a fundamental difference between quantum gates and classical gates. All these classical gates that I write down here have 2 inputs and 1 output. So if I write down a truth table for this and I look at the outputs of these classical gates, I cannot reverse this operation. I cannot go back and say this is the specific input from which I got this output. However, all quantum gates are unitary matrices of some kind, and unitary matrices, maybe you're all familiar, they're all reversible because their adjoint or the complex conjugate transpose of the matrix is the same as its inverse. So all unitary transformations are invertible, so all quantum gates are invertible. So the computational paradigm has now completely shifted from one of irreversible computation. So a classical computation has a particular arrow or a particular direction in which it progresses, and as it goes along, there's no way for you to go back and reverse this. But with a quantum circuit, I can actually talk about running the circuit backward and getting back to where I started, because this entire set of gates are all unitary transformations. So in fact, the correct analog of quantum computing is to actually look at what is called reversible classical computing, which is something that people have studied. Do people know of examples of reversible classical gates?
Like there was one related to XOR.
Yes, related to the XOR, but not the XOR.
It had
Three, correct. So it had 3 inputs. It's called a Toffoli gate. So there are 2 examples of classical reversible gates, the Toffoli gate and the Friedkin gate, and both can be used for universal Boolean logic. So there is a quantum analog of the Toffoli gate as well. So those would be more natural points of comparison between classical and quantum. Okay, anyway, so all of these gates have matrix representations of this form. Since this is a 2-qubit gate, it becomes a 4x4 matrix, because now I have a pair of qubit registers. A single qubit register was a 2-column vector. Another single qubit register is another 2-column vector. But now when I put these two things together, I have to make a 4-column vector to describe all possible states of these 2 qubits. So this is now a 4 cross 4 matrix operation. So all 2-qubit quantum gates will be 4 cross 4 matrix operations. And indeed there is a notion of universality, that is any multi-qubit gate can be implemented using C-naughts and single qubit gates. So this is, I think, as much as I want to say about computation here, but I want to show you an example of a simple quantum algorithm that one can do. And maybe I will stop with that. So the simplest toy problem that you can have, which shows example of what is the advantage of using quantum bits and quantum gates for computation, is this so-called Deutsch problem. So this is what the problem is. It's a 2-player game. So there are 2 players, Anita and Bharat. Anita selects some number between 0 to 2 to the n minus 1, which means she's selecting one of the set of n-bit strings, right? You consider the set of all possible n-bit strings. There are 2 to the n of them. They all correspond to some integer numbers. So she's picking one integer number which can be represented by an n-bit string. Is that clear? And she's sending it to the other player. The other player has a box which can evaluate any n-bit Boolean function. In particular, he has been given, or he prepares maybe, a particular box that evaluates a particular function. Okay? And he only sends the outcome of that back to A. So it's an n-bit Boolean function which maps this n-bit string to a single bit. The input is n bits, output is 1 bit, right? Some sequence of gates have happened inside and the outcome is either 0 or 1. So now the game is that B is going to pick some box which is going to evaluate a function and send the outcome, and A's task is to identify which box did B pick. So what are the options for B? B is going to pick either a function which is constant, which means it has the same output for all inputs, or balanced, which means that it gives 0 for half the values and 1 for the other half. Okay, so B can pick one of these 2 types of boxes. It actually doesn't matter what F itself is, but A's task is to identify whether the box that B picked is a constant function or a balanced function. So whether the function that B was evaluating is a constant function or a balanced function. Okay? So, and the question now is, how many moves does A have to make to win this game? Meaning, how many times does A have to send different binary strings to B, get the outcome? How many times does she have to do this before she can decide whether the function is constant or balanced? So the reason that this toy problem is interesting is it maps to a certain model of complexity in computation called oracle complexity or query complexity. Computer science majors here who have heard of query complexity or oracle complexity? Yeah. So the idea is that you have a black box. So this function or this box that B has to evaluate this function is the black box, and you don't worry about how complex the box is. Meaning you don't worry about what is the space or time complexity of evaluating that function, but rather you worry about how many times can I access this box. And if you know where this word oracle comes from?
Greek mythology.
Yeah, what in Greek mythology?
Whenever the heroes go on a quest, before going there, consult the oracle.
They consult an oracle. So the oracle is this goddess who knows all the answers. So she's in a temple in Delphi, I believe, in Greece. And the point is that she knows all the answers, but you can query her only so many times. So that is where you are constrained in. So your constraint is in how many times you can query this black box, and not really in how complex the box itself is. Okay? So this is this query complexity model. That's what this toy problem captures. So yeah, classically you can tell me how many times does A need to query the black box, or how many times does she need to send different inputs before she can decide
if it is constant or balanced.
That's the promise. You're given that the function is constant or balanced.
2 raised to n by 2.
2 raised to the n by 2.
N minus 1. Whole thing minus 1 by 2. 2
Okay.
and minus.
So basically, total number of strings by half plus 1. Yeah? Because you have to query half this number of strings plus 1 more. Okay. How does that scale with n? Exponentially. Now what Deutsch showed is that in quantum computing, if you were allowed, if the whole game was now being played such that the box, or if A were allowed to access this box in a quantum way, and I'll explain to you what I mean by a quantum way, then A can succeed in a single query. So this exponential complexity, query complexity, has now been reduced to a constant. It's not even linear scaling, it's now constant query complexity, just a single query. So of course the name of the game is superposition. So yeah, classically you have to query this many times, but now you can answer with a single query. So I'm going to explain in words why that happens, and I'm going to show you a circuit which you will need some time to process, but maybe the explanation in words is simpler. So of course the point is that A is going to query in superposition. So how do you query in superposition? So what is the idea is now that this is a kind of box. So this is the kind of circuit that Deutsch came up with, where he said that you can now use this idea that you have multiple qubit registers, you can prepare superpositions. Now because you can prepare a superposition, it is as if you are able to query. So this is my black box. It's as if I am able to simultaneously query this black box about both 0 and 1. Okay, by preparing the superposition. So here's an example of a quantum black box or a quantum oracle corresponding to the classical oracle. So the classical oracle was just computing f of x. The quantum oracle has two registers, x and a y. Now the y just comes along for a ride. Okay, it's what's called an ancillary register. Nothing happens to the first register, it remains x, but the second register, somewhat like that control gate that I explained, changes depending on what f of x is. So y changes depending on what f of x is. So now you can work out that if both were 0, 0, what you get here is 0, f of 0. If this was 1 and this was 0, you get 1, and here I have the second register is now f of 1, right? Because y is just set to 0. So 0 XOR anything is whatever you XOR it with. So in the second register, I am now left with either f of 0 or f of 1, depending on whether the first register was 0 or 1. So by simply preparing a box like this, where I am querying in superposition and I have this ancillary register, I can actually have an output state where I simultaneously have information about f of 0 and f of 1. But there is a catch. What I have written on the final output state is another superposition of both. So this is a superposition of the form 0 f of 0, 1 f of 1. So for the first time we are encountering what we call an entangled quantum state. Because if I now how am I supposed to extract f of 0 or f of 1 out of this? I have to make a measurement. So let's say I measure the second register. If I measure the second register, what do I get? I'm going to get one of these two outcomes. So I'm going to get either f of 0 or f of 1. And correspondingly, the first register is going to be either in 0 or in 1. So if I measure the first register and I get 0, I know that the second register is f of 0. If I measure this and I get 1, I know the second register is f of 1. So these two outcomes are correlated. These two registers are now in a correlated state. So this is an example of an entangled quantum state where the measurement outcome of one is correlated, classically correlated with the measurement outcome of the other. So this doesn't really seem to help. So what is all this song and dance about quantum parallelism? Because after all, if I have to keep doing this in a linear fashion, then again you realize that the complexity is exponential. It's just a different kind of complexity, it's now sampling complexity. Because I have to keep sampling this outcome, then get f of 0, then get f of 1, then I have to XOR f of 0 and f of 1 to know whether the function is constant or balanced. This is a single qubit version of that game, right? So how does this help? The point is, now I don't measure. Instead what I do is I interfere these two states. So I have a superposition here. Now think again in terms of light. Now when I have your double slit experiment, you have light coming out of these two slits, and then you make these two different beams of light go and meet at one point, and then you have a dark or a bright fringe depending on some relative phase information. So that's what we're going to do in the actual outcome. Sorry. So yeah, this is all I've said here. So the actual algorithm needs a bit more than just that oracle or that black box. You make a single superposed state. Now you have a black box which is going to evaluate multiple values simultaneously. Yes, fine. But now you don't get access to all those multiple values individually. So you have to now interfere the states in that superposition. I will show you what I mean by that. And then a single measurement can tell you whether the function is constant or balanced. Note that the task was not to identify the function. The task was not to say give me f of 0, give me f of 1, because the quantum algorithm cannot give you that. The quantum algorithm can only give you some function of f of 0 and f of 1. In this case, the function you're looking for is actually the XOR of f of 0 and f of 1. Because if XOR of f of 0 and f of 1 is 0, you know that the function is constant. If the XOR is 1, you know that the function is balanced. So what you're looking for is a global property of this function, that is f of 0 XOR f of 1. You're not looking to find out what is f of 0, what is f of 1, because that information is there. It's there somewhere in your quantum black box, but you don't have access to it because it is sitting in superposition. So the best you can do is perform some kind of interference using quantum gates and get access to this non-local property. By local I mean value of f of 0, value of f of 1. You don't have access to that. You can get a global property out, and that is what the Deutsch-Joza algorithm tells us. So Joza, by the way, is Richard Joza, a computer scientist, and this is perhaps one of the first examples of a physicist and a theoretical computer scientist collaborating together to come up with a quantum computing algorithm. So here is the difference. So you see the difference from the previous slide that I showed you. This second register is now in a superposition state also. Okay? And by making the second register in a superposition state, it is as if you have put these two slits of a double slit experiment. And finally here, you do a particular quantum gate called the Hadamard gate. I can tell you more about it again if you want. It's a single qubit gate, which essentially acts as an interference device. And then if you measure, it turns out that the state here, right, actually is different depending on whether f of 0 is the same as f of 1 or not. So this information about f of 0 versus f of 1 is something that you have mapped onto a relative phase of the first register. Once you have mapped something onto a relative phase, you can do a quantum measurement to identify that relative phase. In this case, you have to do a Hadamard gate, and then you measure in the 0-1 basis, and you can actually get this information about whether the function is constant or balanced. So I've just written out the steps here, but yeah, measuring the first register, A gets to know whether f is constant or balanced. So this is a single qubit example. In the single qubit case, the classical algorithm needs two queries, because A has to find out f of 0, A has to find out f of 1, and then decide whether f of 0 is the same as f of 1 or not. That is the XOR operation. In the quantum case, single query. So the speed up is not dramatic when you look at the single qubit case, but it turns out you can repeat the same thing in the n qubit case, where again you prepare a superposition here, except your register is now an n qubit register. You need only a single qubit ancilla. You do the same thing. Now you have a massive superposition of 2 to the n states here. You run this once. You again do this interference gate, that is the Hadamard gate, and you measure. And again in a single shot, you can get this answer about whether the function is constant or balanced. So there you really reduce the query complexity from exponential to constant. Any questions about this?
Ma'am, is there any work on reducing the number of edges we need?
Here?
Yeah.
So in this particular example, you really can't. If you do that, you will probably have a trade-off with the query complexity. Right? So there could be a trade-off between space and query complexity, and that is something that people have studied a little bit.
Algorithms, we have a time space trade-off.
Yes.
Or do we have a query register trade-off?
Yes, you could think about a query register trade-off here, and that is something that people have studied. If you look at lecture notes by John Preskill, there is an interesting problem about this involving the Deutsch-Jose algorithm, where he asks you to explore essentially this aspect. Okay, so yeah, other examples, I guess people may have heard of these kind of examples. So searching becomes quadratically faster on a quantum processor, factoring becomes exponentially faster on a quantum computer, and there are algorithms for all this. More recently, so these were all algorithms that were developed in the 90s. More recently, it was shown that solving a system of linear equations in n variables again has an exponential speed up in the quantum case. So indeed, there are several practical algorithms which are expected to run exponentially faster in a quantum computer. So this is sort of the complexity landscape at this point. This is from Scott Aronson's blog, which is a very nice thing you should follow if you are not following already. So classically, we know of all these different classes. You have P, and then you have NP, and then you have this hardest problems in NP, the NP complete. Factoring is known to be or thought to be in NP, but not NP complete. And we have an exponentially fast algorithm quantumly for factoring. But we don't yet have any example of a quantum algorithm which is exponentially faster than classical for an NP complete problem. Okay? So instead, the quantum landscape looks something like this. So this is the quantum analog of the P. P is polynomial time. This is bounded quantum polynomial time. And this BQP is something that overlaps P and NP, right? Which makes it of interest to computer scientists as well. However, it is not known to stretch into the NP complete region, and that's a big open question whether there can be an NP complete problem that can be solved exponentially faster or not. So this is where we are at, and we are at 1:15, so I think I should stop here. I'm happy to take questions, but I just want to show one last slide about the current landscape of quantum computing itself. Just a couple of minutes. So again, this is from a recent blog post which you can read. So this is basically telling you where is quantum computing today. So I think I showed you what qubits are, how do you compute with them, and an example of a quantum algorithm which had exponential speed up over the classical case. But if you really want to do all these nice things like RSA and so on, then what do you need? So by the way, just a couple of days ago there were papers which revised this estimate and pushed it further to the left. But what is here is the number of qubits going as a million qubits. You see RSA 1024, it says you need about a million qubits. And what's on the y-axis is something called the error rate, and you realize that this is actually decreasing as you go up along the y-axis. So this error rate you can think of as the probability of failure of a single qubit, or meaning the probability with which now remember all this algorithm and everything, the computation is all on the surface of the Bloch sphere. So you need your qubit to constantly keep living on the surface of the Bloch sphere. So this is where the question that you asked, that what is inside the Bloch sphere, becomes very important, because there are constantly physical processes that keep mapping you from the surface to the inside. And when that happens, you lose coherence, right? So in the case of so you can think of this error rate as essentially the probability with which you get mapped from the surface of the Bloch sphere to the interior of the Bloch sphere, or the probability with which a particular gate that you wanted to do didn't do exactly what you wanted it to do, etc. So you see that the kind of error rates that you need are about 2 orders of magnitude lesser than where the present day hardware is. So this little grey box here is where all the processors of today are. They are at about between 100 to 500 qubits. This is IBM, this is Google, this is IonQ, Quantinuum, different kinds of physical realizations of qubits, and their error rates, maybe Google has some of the best ones at 10 to the between n-2 to -3. Rigetti promises even lower and so on, but they are, I'm sorry, Rigetti is even higher, I want to say, yeah. The Prabha ones are even lower. So this whole thing has to really be pushed up, somewhere of the order of 10 to the -4. So to reduce the error rate by 2 orders of magnitude, increase the number of qubits by 4 orders of magnitude, and that is where you start realizing useful quantum computation. So there's a big gap out here, and we believe that this gap can be bridged using something called quantum error correction, and that is what I work on, and I have had no time to tell you anything about it. But if you're interested, I'm happy to talk about it some other time. There's a very nice article here, Mind the Gaps, the Fraud Road to Quantum Advantage. Came out last October. It's a very nice article to read. An earlier article also, these are all, I'm pointing out to some of these articles which may be accessible to people who are not experts, but you know some of the jargon which I have told you now. So with this, I'll stop and happy to take questions. Yeah.
Are there problems which cannot be solved by classical computers and all can solve by quantum?
What do you mean by cannot be solved by classical computers?
No, like in the
everything is a computation file. It's a question of what kind of resources you need to solve it.
Like in the diagram, you showed that there was some region outside of, in the diagram which you showed of the PH.
No, well, I mean, that's more a cartoon picture. It's not that, well, you can say that there are problems for which you don't know the complexity of the classical algorithm, right? So one example of something like this is something called quantum simulations. That is, if you want to really simulate a physical system, like a many-body physical system, right? You need lots of resources to do this in a classical computer. You don't have very well-defined scaling for these algorithms because these are what are called heuristic algorithms. Like you expect that the algorithm will scale in this way, but if you're clever and if you kind of manage to reduce the number of parameters you need to describe the physical system, then maybe you can do it with fewer resources. So there's no well-defined scaling for some of these simulation kind of algorithms. Like if you want to simulate quantum field theories on a classical computer, if you want to solve quantum chromodynamics on a classical computer, if you want to solve lattice QCD, what's called lattice QCD. So this was Feynman's original sort of thinking, that nature itself is quantum. So why are we trying to solve quantum field theories on a classical computer? If we had a computer that could mimic nature in the sense that do quantum computing, so he was a sort of one who came up with this idea, right? And his original thought process was along these lines, that if I want to simulate something like lattice QCD, which was one of the biggest problems of his times, the 80s, classical computers were at their limit, right? So his idea was that if you could have a quantum computer, one which would naturally work, one which would actually naturally operate using the laws of quantum mechanics, then these problems should become easy, right? So today there are indeed quantum algorithms for simulations. There are quantum algorithms for simulating quantum field theories, and some of them indeed have very nice complexity scaling, but many of them are again still heuristic. So it is not clear where or how much quantum advantage you actually get there, but heuristically it does seem that we do get a lot of quantum advantage when you try to simulate what's called a many-body physical system on a quantum computer versus a classical computer. So that could be one example of a problem for which you don't have a well-defined complexity class. Questions? Okay.